Hello, my name is Clara Meister. I'm a PhD student at ETH Zurich, and here I'll be presenting a new stochastic decoding strategy for structured prediction models called Conditional Poisson Stochastic Beam Search. So I'll start off by giving a brief overview of the tasks for which our decoding strategy is relevant, namely tasks involving structured prediction. Many of the core tasks in natural language processing involve some sort of structured prediction. For example, any one of the many language generation tasks, or parsing. In these tasks, we can generally think of our structured prediction models as black box functions that assign a score to an output sequence that's dependent on some input. In the case of probabilistic models, this is usually just the conditional probability of the sequence under the model. We'll use the more general score notation, though, throughout the rest of this presentation. Now, at inference time, our goal is typically to find the highest scoring output y from our set of possible outputs. This is known as the decoding problem, or for probabilistic models, maximum a posteriori inference. Now, in structured prediction tasks, our output space is typically exponentially large. Like in language generation, it's the set of all possible strings that can be generated from a model's vocabulary. Now, because today's neural sequence models are typically non-Markovian, brute force search would lead to a combinatorial explosion. So instead, we use heuristic search methods to solve the decoding problem, like beam search. So, a bit of background. Beam search is a widely used heuristic search method for decoding structured prediction models. Beam search can be seen as a pruned version of breadth-first search. It limits the number of paths we explore by pruning the search space down to the top k options at each turn, where k is a hyperparameter. Now, beam search is a deterministic algorithm, meaning it always returns the same result for the same score function. But what if we want a diverse set of outputs? Or what if we want to build statistical estimators for expectations under our model? Well, what happens when we use standard set decoding algorithms like beam search? So, as we were talking about, beam search chooses items purely to maximize the total collective score of the set. Under typical settings, there's no incentive for coverage of the output space or intraset diversity. Due to the local normalization scheme used by many probabilistic models, the resulting items often have high overlap, such as the set shown here. Additionally, the deterministic nature of the set means that when working with probabilistic models, the samples can't be used to build statistical estimators for expectations under our model. Rather, any estimator that we build using these samples is likely to give us a highly biased estimate. So, how can we solve these problems? Well, first, let's take a closer look at what the beam search algorithm is doing. We can concisely write beam search as an iterative process that finds the highest scoring set under a specific set function at each time step. Here, we define the set function as simply the product of individual item scores. Now, our search is limited to items on the beam. That is, the set of extensions of the top k items from the previous iteration. And further, we perform the search for a set number of iterations, or until all items on the beam are complete. Now, this argmax operation here is arguably the root of the problems we were just discussing. It's what makes the final set deterministic and is a factor in the lack of diversity typically seen in the final set. So, what would happen if we replace this operation with a stochastic process? Specifically, what if we instead sampled from this set function, while enforcing the same constraints on size and candidates? Well, it turns out that sampling size k sets without replacement proportional to this function is actually just a form of conditional Poisson sampling. Now, I won't go into details here of the conditional Poisson sampling design, but we provide a brief overview in the appendix of our paper for those interested. So given this relationship, we term our new form of beam search conditional Poisson stochastic beam search. We view our algorithm as the natural stochastic alternative to beam search. In fact, we recover standard beam search under a very basic case, when our local sampling distributions are annealed with a large enough temperature parameter. In that case, we will necessarily choose the argmax set. The same connection exists between greedy search and ancestral sampling, actually. Unlike beam search, though, we can use the final set from our stochastic algorithm to build statistical estimators. Further, the stochastic nature of the algorithm leads to a more diverse set of outputs generally. So now I'll give an informal overview of the mathematical details of the algorithm. For a more rigorous treatment of these details, we invite you to look at the paper. So first, how do we turn our set function from earlier into a sampling distribution? And subsequently, how do we sample from it? Well, let's rewrite the piecewise function in a more general form, using a weights function w instead of a model-specific score function. And let's give the corresponding sampling distribution a name, cube sub t here. A closer look at this distribution shows that naively computing the normalizing constant would require summing over exponentially many summons. Fortunately, we can use dynamic programming, reducing this computation to O of nk time, where n is the size of our beam set. Using the results of this program, sampling can be done in just O of n time. The next detail of interest is how to choose our weights function. So our weights ultimately determine the probability of any given item being included in the sampled set at each time step, also termed an item's inclusion probability. Of course, we can just set weights to the score of an item under the model, as we suggested earlier. But the resulting inclusion probability is not necessarily proportional to this quantity. If we want to explicitly determine inclusion probabilities, we can choose appropriate weights via numerical optimization, or we can use an approximation for efficiency. So now, on to building statistical estimators with our resulting sets. From now on, we'll assume we're dealing with probabilistic models and switch it to the p theta notation. So, as mentioned earlier, we may wish to estimate the value of an arbitrary function under a probabilistic model. Such estimators are often used in learning algorithms like reinforce or minimum risk training. The deterministic set generated by beam search will likely give us a highly biased estimate of the value in question. However, using the Horvitz-Thompson estimator in conjunction with our sampled set would give us an unbiased estimator. Note that in order to build this estimator, we need to know inclusion probabilities for the items in our final set. That is under the iterative procedure whose distribution over sets we denote as capital P. This isn't just the specific time step inclusion probability that we discussed earlier. So how do we compute inclusion probabilities? Well, the inclusion probability of any given item can be seen as the combined probability of all sets containing that item. In many of the settings where structured prediction models are used, though, this sum would be intractable. So instead, we efficiently estimate these probabilities. Now, the obvious way of estimating an inclusion probability would be to just sample a bunch of sets from P and take our probability estimate as the proportion of sets that contain the item Y. However, we may have to sample a very large number of beams until we eventually sample one that actually contains Y. If we're trying to keep our number of samples reasonable, then our estimate of the inclusion probability for where Y will often be 0. And the big problem here is that in our Horvitz-Thompson estimator, we need to invert inclusion probabilities as they're the values in the denominator. And of course, we can't invert 0. So our Monte Carlo estimator isn't a good option. But it turns out that we can use a different, more efficient approach to estimating inclusion probabilities. So let's consider a distribution tilde p. And this distribution only places probability mass on sets containing Y. So if these sets are sampled proportionally to our original P, then it turns out that the product of per time step inclusion probabilities, according to our original sampling distribution, gives us an unbiased estimate of our inclusion probabilities. So note that since we need to invert inclusion probabilities for use in our Horvitz-Thompson estimator, it's no longer the case that this estimator is, that the Horvitz-Thompson estimator, that is unbiased. However, it will be consistent, and further, we see empirically that it's typically much lower variance than a standard Monte Carlo estimator. So now I'll present some empirical results using our proposed estimator. In these experiments, we estimate BLEU and conditional entropy of machine translation models. We set weights to give us inclusion probabilities approximately proportional to probabilities under our model. We additionally use a temperature parameter with the local sampling distributions to mimic both high and low entropy distributions. We compare estimators to several baselines, including the estimator proposed by Kuhl et al. With their stochastic beam search algorithm, as well as the sum and sample estimator and a basic Monte Carlo estimator. We provide more details of the setup in the paper. So we see that in general, our estimator, denoted by the purple line, is much lower variance than the other estimators, as indicated by the shading. Now, this is a very desirable trait for use in some of the learning algorithms we discussed earlier, where high variance estimators negatively affect convergence, among other properties. So further, we see that the root mean squared error of our estimator is also generally low. Although similar to other bias estimators, we see effects of biasness in high entropy settings. Rather, as we should perhaps expect, a basic Monte Carlo estimator is usually the best choice in these settings. So, with that, thank you for watching, and here's a link to the paper for those interested in more theoretical and empirical results.